Hello everyone, welcome to a new video. And this video is about gas-vapor mixtures and dedicated to air conditioning. This video is a preliminary video about the working principles of air conditioning. So let's discuss air first. What is air? Well, air is actually a mixture of all kinds of gases, so nitrogen, oxygen, carbon dioxide and whatever. Of course there's a bit of water vapor inside air. And when we're discussing air conditioning, we're especially interested in the amount of water vapor that is in air. So in this series of lectures we're going to discuss atmospheric air. And we assume that atmospheric air consists of dry air and water vapor. In these lectures we will learn that this water vapor is especially interesting since we will be talking about humidity, so the amount of water vapor that's in the air, and we want to keep this as comfortable as possible using air conditioning appliances. So that's what we're going to discuss in detail. For now, under conditions that are usually considered for air conditioning, and these are in air conditioning applications, these are usually temperature between minus 10 degrees Celsius to 50 degrees Celsius, and of course the pressure is assumed to be atmospheric. So we're going to consider everything at atmospheric pressure, and well, in this situation we can assume that both of these are ideal gases. From dry air we already know that the enthalpy, and this will be used later, so I'm just going to state it, of dry air, which is H subscript A, can be described by the constant pressure, since we're at atmospheric pressure, multiplied by the temperature, since it is an ideal gas. And for water vapor we actually can use a similar relation, but we're going to derive this at atmospheric pressure. And before we do this we need to use Dalton's law. I will write it down. Dalton's law basically says that the pressure, the gas pressure of a mixture, so we're talking about mixtures, so the pressure of a mixture can be described by the pressure of its individual components. So like air consists of a lot of different gases, so all these gases contribute to the pressure of air. So it goes from substance I to substance K. In this case, in this lecture we assume, in this video we assume that there's only dry air and water vapor inside the air. So we are only considering air and water dry air and water vapor, and it has a certain pressure and a certain volume. So this is what Dalton's law says. And in our case this will result in the pressure. So atmospheric pressure consists out of the pressure of dry air plus the pressure of water vapor. So, and this is, this is the vapor pressure of water, T atm and V atm. So this is the water pressure, the vapor pressure of water at atmospheric pressure and atmospheric specific volume. And this of course denotes water vapor, and this is the dry air pressure. And this actually is the pressure of the ambient pressure, so the pressure of the surroundings, and consists of the pressure of dry air and the pressure of water vapor. Okay, and we are especially interested in humidity. So the amount, and I'll just write it down, humidity, and that is denoted by omega, and that's equal to the mass of my vapor divided by the mass of dry air. And so this is the specific humidity, and it actually says the amount of vapor, so the mass of vapor that's contained within a certain amount, a certain mass of dry air. In air conditioning, not only temperature matters, but the amount of vapor inside the air will give you a certain feeling of temperature, a certain experience of temperature. And that's why we often want to regulate the amount of vapor, water vapor, that's inside the air. Well, and if we do our physics correctly, this will lead us to this relation. The pressure well, if we do the maths correctly, it will lead us to the pressure of the vapor defined by the pressure of the dry air. So the specific humidity is a measure for the amount of vapor inside the air. And there's another relation that indicates something about how hot or how cold it will feel inside some room based on the humidity. And that's actually the relative humidity. And that's denoted by phi, and that's equal to the mass of the water vapor that's inside the air divided by the mass of a gas. And I need to explain this. So this is the relative humidity, and this mg is the amount of water vapor the atmosphere can contain just before condensation. So I will write it down. So if I would add more water vapor to this mixture of air, so there will be more vapor than the mg, then that's not possible. The air can't contain this, so it will immediately condense. Well, and if I do my mathematics correctly, this will result in this relation. So it's similar to this. That says, well, it's PV, so the pressure of the vapor divided by Pg. Well, I think we're all familiar with Pg, because this is actually P set, so the saturation pressure at, well, the T, for instance, the T of the temperature of the room or whatever. And well, this relative humidity gives some indication, because if, for instance, so if my PV and therewith mv is 0, and the relative humidity will be 0, and that will result in dry air. So there's no humidity whatsoever. And if this PV is lower than P set, so actually Pg, then it's unsaturated, so I can add more vapor and saturated, and if PV is equal to Psat, we know that the whole thing is saturated, and if I add more saturated, and if I add more liquid to the room, for instance, somewhere it will start to condense. Okay, now we have discussed the relative humidity and specific humidity. We of course are very interested in the amount of energy we need to add to a system, or the energy the system contains when air conditioning. And therefore, of course, we need to know something about enthalpy. And unlike what you're used from us, we won't discuss the specific enthalpy, but we will discuss the total enthalpy, which is H, so of a certain system, a certain volume, that's equal to the enthalpy of the dry air plus the enthalpy of a vapor. And of course I can make this specific because that's way easier. Then I'm not dependent on the volume and the mass of my room. So that boils down to. Now I'm going to do something what I think is really clever. I want to get rid of my MA. So I'm going to divide everything by MA, and it will result in this. My enthalpy, my specific enthalpy of my entire system, H, is equal to MA over MA, because I'm going to divide by MA, so it will result in HA, plus MV over MA, that's omega, and HV, of course, will remain over there, HV. And this is actually a very convenient relation. Now I know that the total enthalpy can be described by the enthalpy of dry air, which I can easily define because that's over here, and the specific humidity multiplied by the enthalpy of my vapor. So this enthalpy of my vapor can easily be described because it's the enthalpy at some temperature T, and it is at a low pressure because we're considering air conditioning applications, and it's usually at low pressure, atmospheric pressure. Now, it's not very high, and then we can assume that this is equal to, or it's really close to the enthalpy of my gas at a certain temperature. So let's look into our diagram. Over there, if I would check for the enthalpy, and I've got 50 degrees Celsius over here, that's our maximum temperature. If I would look at my diagram, the enthalpy lines, the lines of constant enthalpy, look like this. So over here, along these lines, H, enthalpy, is constant. So I can be pretty sure that my enthalpy of my gas is constant, and the variation between the enthalpy for the vapor itself and the gas, they're only very minor. In the purpose of speaking, of explaining, it's usually very convenient to talk about the dew point. So I'll discuss that over here, the dew point. So the dew point is the temperature at which condensation occurs when at a constant pressure and the air cools. So let's see how this looks like in the diagram. I'm at a certain pressure, so here we've got an isobar, so we've got a specific pressure, and we're going to cool the air, so we're going to drop in temperature. We're over here, and we're going to cool. Then over here, this temperature at which water condenses, this is my dew point, T dew point. And we know that when my dew point is, for instance, 25 degrees, that water will start to condensate at 25 degrees. So if water starts to condensate at 25 degrees, we know that when it's 25 degrees, which is actually pretty warm, that we've got 100% of humidity. So, well, I think now over here it's 25 degrees, so it would be very humid right now. So, yeah, that's what the dew point says. And the dew point is actually, it is the dew point, which is the saturation temperature at a certain vapor pressure. So these are the basics of gas vapor mixtures, and this is everything you need to know before you start designing air conditioning applications. So good luck, and see you in the next video.